This is the tutorial for the Falling Bodies lab. In this lab, we'll be learning about how objects respond to gravity here on the Earth. But we'll also be learning about measurement and uncertainty. We'll study the limits of what we can measure and some of the techniques scientists use to overcome the uncertainties inherent in the ways we measure things. The first part of this lab looks at the limitations of how well we can measure things. Every measurement we make has a built-in uncertainty. A simple way to see this is to consider measuring your height. You probably know how tall you are to the nearest inch, or maybe even half inch. But you probably don't know how tall you are to the nearest hundredth of an inch. It's unlikely you've ever measured your height with a ruler that was that accurate. And even if you did, your height changes by more than that over the course of a day. So it's probably different now than it was the last time you measured it. The most common way to describe the uncertainty in a measurement is with the plus-minus notation. You put the best estimate value first, then follow by a plus-minus symbol, and then estimate the uncertainty of that number. So, if you measure your weight on a digital scale as 171.2 pounds, but it could be as much as half a pound more or less than that, you would write your weight as 171.2 plus or minus 0.5 pounds. This says that the value could be as little as 170.7 or as much as 171.7 pounds. Notice that the last digit in the weight, the 0.2, is the same number of digits past the decimal as the uncertainty, the 0.5 pounds. We wouldn't want to write this as 171.2000 plus or minus 0.5 pounds because 171.2000 implies that we know the number much more precisely than we do. So this is an important idea to remember, not just in this lab, but throughout this course. Don't write down lots of extra digits when you're measuring or calculating values. When you're recording a measurement, make the last digit be the one you're uncertain of. If you're doing calculations, try not to give more digits in the answer than the number with the least digits that went into the calculation. There are many different possible causes of uncertainty in a measurement, but generally we divide these up into two major types: random and systematic errors. Random errors are errors that are equally likely to give you an answer that is too large or too small, and tend to fluctuate between the two. In the example we described earlier in measuring your weight on a scale, if you measure several times, you might find that your weight bounces around a little between several different values. In that case, it's just as likely that the value we first saw, 171.2 pounds, is a little bit big or a little bit too small. Random errors are especially important when there's a built-in fluctuation in what we're measuring. If you're measuring your weight, you might get a collection of measurements that looks something like this. Since you've got a fluctuating set of data, you could find the average of these points and say, that is my weight. The real value might be a little bit more or a little bit less than this. So you could use the range of fluctuations to determine the uncertainty in the measurement. This is an effective approach to dealing with random errors. Note that the approach we're describing here gives you a start on estimating the size of a random error, but it's possible to do much better than we've described. Large parts of the study of statistics were originally developed to allow people to more accurately estimate the size of uncertainties in measurements with random errors in them. We're not going to go through those here, but if you've learned these techniques in other classes, you're welcome to apply them. In contrast, systematic errors are ones that are systematically too big or too small. In the example of measuring your weight, you might have a scale that is set incorrectly so that it always reads your weight as a couple of pounds too large. Many people report that they have scales like this. Note that in that case, You can keep measuring as many times as you want, but the answer will still be too large. Averaging over several measurements doesn't help. Systematic errors are much more challenging to handle than random errors. There isn't a general mathematical trick you can apply to minimize their effect. Instead, you have to think carefully about how your measurements are being made and try to find any places that could introduce a systematic error. Systematic errors can come from a number of sources, including human reaction time, problems with equipment, and people's tendency to miss effects that they aren't expecting or that don't show up very well. An example of this sort of bias in astronomy comes from observing stars. When you look at the night sky, you see the biggest, most luminous stars in our part of the galaxy, while missing the much fainter stars that actually make up most of the stellar population. Have a look at the 4 dartboards at the end of this section and see if you can decide what effect random and systematic errors are having on each of them. Now it's time to start working on your experiment. The idea in this experiment is that you will measure how fast it takes a body to fall from different heights. We can use this to estimate the acceleration due to the Earth's gravity. If we had very accurate measuring equipment, we could do this experiment just one time, and it would tell us the Earth's gravitational acceleration. However, since this is a real-world experiment, we're going to repeat it several times from different heights and see what that does to the results. This will let us explore some of the sources of uncertainty in the measurement. You're going to need something you can drop from different heights. I suggest tennis balls, but you're welcome to use anything you have available that you don't mind dropping and that is heavy enough that it won't be slowed down a lot by the air. You want to have at least 3 different heights you can drop things from. The higher you can safely do this, the better. If you have an opportunity to drop things from a 2nd or 3rd story location, that's great. But only do this if it won't involve any chance of injuring people or property. If that's not an option, even standing on a chair and dropping from as high as you can reach up can help. You'll need a way to measure the height. If you have a long enough tape measure, that would work. But the lab also describes how you can do this with a string and a weight. Just hang the string with the weight from the drop location to the ground and mark the string. Then you can use a ruler or meter stick to measure how much string you used. You'll need a way to measure time accurately. Stopwatches work well for this, and many phones now have a stopwatch feature on them. You can also take a video of the drop and use video software to review the time it takes. This brings up an important point. This is a challenging lab to do all by yourself. If you have the chance to get some help from a classmate, family member, or friend, it will make the lab much easier. When you're ready, you can start dropping your objects. Make sure you do at least 3 drops from each location, recording the time for each attempt. You might want to do a couple of practice runs to start with just to make sure you and the person you're working with have got your system of dropping and measuring the time worked out. Also, don't forget to measure the height of each drop. Note that the table asks for heights in centimeters, so if you're getting the heights in a different unit, like inches, you'll need to convert them. Remember that 1 inch equals 2.54 centimeters. Fill in the times and heights in Table 1 in the lab write-up. As you do your experiment, think about what makes it challenging. How confident are you about measuring the heights? How much does the reaction time of the person dropping and/or timing affect your results? Note that there's a link in the lab to a reaction time tester you can use to see how big an effect reaction time has. Compare this to the measured times and decide how big a role reaction time is playing in the times you're measuring. Also try to decide if the uncertainties are systematic or random. Once you've measured the times, take the average of the 3 values for each location you drop from. Remember that to find the average of three values, just add them together and divide by 3. Then square the average time to find the average time squared at each height. You'll need this in your calculation of the acceleration of gravity. Finally, don't forget to answer all of the questions at the end of this section of the lab. The next step is to create a graph of your data. The instructions are set up for doing this on a spreadsheet program, but you're also welcome to create it by hand if that's more convenient for you. You want to have the height on the vertical axis and the time squared on the horizontal axis. You can do this in a spreadsheet by placing the time squared values in the first column and the height values in the second column. Also add the 0 second squared and 0 centimeter point at the start of your list, since you know that it doesn't take any time for something to fall from 0 centimeters height. Then select all the data and use the scatter plot option to create the graph. There are many spreadsheet programs that get confused if you select the header rows where you might label the columns, so leave those out of your selection. Have a look at the scatter plot and make sure it looks like your data. Check a point or two and make sure they really reflect what the numbers say in the table. Sometimes if there's a problem, the spreadsheet will ignore one of the columns and just plot the points in order with even spacing instead. Use the program's labeling functions to label the vertical and horizontal axes. Don't forget the units, centimeters and seconds squared. Also put in a title for the graph. The last step in the skill building part of the lab will be to use the graph you've made to find out how fast gravity accelerates a falling body. To do this, we need to find the slope of the line made by your data. Note that the points will be scattered around this line, so don't try to connect the dots. The scatter reflects the uncertainties in your measurements. Also, if you can, try adding a linear trend line through the data using the spreadsheet's function. If you can't do that, you can use the maximum height point to find the slope from the 0, 0 point up to there. Once you find the slope of the line, you can multiply this by 2 to get your measured value of the acceleration due to the Earth's gravity, g. This has units of centimeters per second squared. Finally, you can compare your results to the accepted value of 980 centimeters per second squared to see how close you got. Use this formula to find the percent difference between your measurement and the accepted value. If you've got a large percent difference, have a look back at your measurements and your graph and think about what may have caused this. The second half of this lab is an exploration experiment. Don't be fooled by the fact that you're not seeing detailed instructions here. In an exploration experiment, you have to develop the procedure yourself, just like the professionals do. This part is as much or more work as the part we've done, so give it the time it needs. The goal here is for you to apply the techniques you've developed in this lab to a question you can explore yourself. You're welcome to come up with your own exploration experiment, but if you do, you should probably check it with your instructor to make sure it's doable with the tools you've got. If you don't have your own suggestion, we've listed several possibilities here. The first option is to try redoing the falling bodies experiment, but changing up the parameters. The idea is to see what happens if you change the shape, size, or mass of the falling body. Note that you don't have to vary all of these. Just pick one or two and test how they change the response. Remember to do multiple drops and think about where you got the most accurate results in the first part of the lab so that you're not being overwhelmed by things like reaction times here. The second option is to try to improve on the experiment. Think about ways you can make your measurements more accurate, either by changing what you drop, how you drop it, or how you measure the time or distance. Then go ahead and redo the experiment to see if your changes improve the result. The next option ask you to go back to another lab we've done and see if you can estimate the uncertainties in any measurements you've made. You should start to look for how uncertainty applies anytime you measure something. Finally, if you've had statistics, see if you can apply what you learned there to the measurements we've made in this lab. Whether you pick one of the options we suggest or come up with your own, you'll need to do a write-up that includes your question and a hypothesis that says what you expect and why. Then you'll want to describe all the steps you take. This should be the sort of detailed, step-by-step description that would allow someone else to duplicate your work. Your write-up should also include all of the data you take and, if appropriate, put in some pictures of your experiment. Finally, include your conclusions where you discuss whether the data supported your hypothesis or not and what went right and wrong in your exploration experiment.